So our next
Hey,
talker is Georgina from the University of Auckland. And yeah, you can get started.
so I'm going to be talking about labeling coset graphs. It's kind of in a vaguely similar idea as the last talk, in that we're going to be turning things into pictures. So we're scrolling apparently. I don't know. So this was part of my PhD, which was supervised by Marston Conda. And for that, I wrote a program in Magma called Graph Labs, very original. And it uses the theory behind the Reidemeister-Schreier rewriting process and seeks transformations to create a labeled coset graph. The labeled coset graph can then be used for rewriting, but it can also be used to find expressions for subgroup elements in terms of given generators. And to demonstrate it, we used it to find nice generating sets for normal subgroups of ordinary triangle groups associated with some regular and orientably regular maps. So there's a lot of words in that first section. So I'm going to go through some vague definitions that are very fast and loose, but I feel like wordy definitions, no one's going to take it in anyway. So a map is a two-cell embedding of a connected graph or multigraph into a surface. I think of it as a planar graph, but in 3D, so it can be on any surface. And an orientable map is a map that's embedded into an orientable surface. And if the surface is non-orientable, so is the map. The genus of a map is the same as the genus of the surface. This definition is pretty confusing, I find. So a map is called regular if the automorphism group is transitive on the flags, and an orientable map is called orientably regular if the automorphism group is transitive on the arcs. But a map can be orientably regular and not regular, and it can be regular but not orientably regular. Either way, the automorphism group has to act transitively on the vertices, edges, and faces, which means that all the faces have to have the same number of edges, say P, and all the vertices, sorry about my dog. All the vertices must have the same degree, say Q, and then PQ is called the type of the map. So there's two types of orientably regular maps. If there is an automorphism T that reverses an edge but preserves the incident faces, then the map is called reflexible, and otherwise it's called chiral. So a reflexible map is a regular orientable map, and a chiral map is an orientably regular map that's not a regular map. If that makes sense. Is everyone with me? Vaguely. Okay. The next thing we're looking at is rotation groups. So the rotation group of a regular orientable map has index 2 in the automorphism group. But for chiral maps, it's the full automorphism group. So you can kind of think of it as you've just taken that T out. So that automorphism that switched the reversed an edge. Triangle groups. The ordinary triangle group or von Dijk group is the group DLMN. It has this presentation. And I'm not going to go into any details here, but you can construct an orientably regular map of type PQ from a quotient of D to PQ. So this would be the ordinary triangle group associated with that map. Now that we've gone through all those definitions, I can tell you what we actually did. So if N is the torsion-free normal subgroup of D, such that the rotation of the map is isomorphic to Dn. And we've found nice generating sets for N. 2G generators, where G is the genus, which is the minimum that you can have. And then you can show that N is normal with our Coset graph just by finding the conjugates. So I'm going to go through a simple example of one of the maps that we did to kind of show how the whole algorithm works. So the map that we're going to be looking at is called R26, and that's from Conj's list of regular maps, which is on the University of Auckland website. So it's type 88. Don't worry about this too. The automorphism group has order 16, but this is a reflexible map. So the group that we're looking for is going to be order 8. And we're taking everything except that T. So from the defining relators, we're taking the ones that don't have T in them. So that's our R. And you can see that's the associated ordinary triangle group is this D, because it's type 88. And the nice generating set that we found is these 4 elements here. So this R is the little r is the elements that have to be in N, but then N also has to be order 8 and normal. And you can see that I've taken the R conjugates of the first element of the little r, and just the first 4 R conjugates, and taking that as my generating set. So that's what makes it nice, is that it's R conjugates. So half the work in showing it's normal is already done. There's not really a definition for nice, it's just nice. Okay, now to try a Coset graphs. So it's a graphical representation of a Coset table. The vertices correspond to the cosets, and the edges are like the kind of correspond to the columns of the Coset table. So HG is incident to HG, HGX for the generators of G, and also an edge for each of the inverse generators. Now I promised pictures. Here's the first picture. So this is our Coset graph of N for our map. You can see it's order 8, so we've got our 8 cosets. I mean, it's index 8, sorry. And we've got 4 edges incident to each vertex. We've got an R going in and an R going out. Those are in blue, and the pink edges correspond to S as one of the generators of G, and we've got one going in, one going out. So this, you're probably wondering why it's not actually the same color as the colors at the top. That's because this is the graph that we're going to label. So I've just put the edges that aren't labeled are kind of like washed out. To get to the point where we're labeling, we need to go through a few more definitions. So a transversal is basically just a set of representatives for each coset. So that could be if you go back to this one, I've got, this is the identity, then R squared, etc. That's, those powers of R are a transversal. And a Schreier transversal is just a sensible transversal. So we haven't taken some long word that is equal to the identity for H. We've taken the identity. And a spanning tree in the Schreier-Coset graph corresponds to a Schreier transversal for the subgroup. So we're going to see a different transversal for this subgroup. So we start with H, which is putting the identity in our Schreier transversal. And we go through and look at the edges that are incident to that. So if we take this blue R edge and add it to our spanning tree, then it's equivalent to adding the element R to our Schreier transversal. And we can go through and add an S edge, which adds S to the Schreier transversal, R inverse to the Schreier transversal, then S inverse. Now, if we go from RH to R squared H, because we've already used R to get to RH, then we're actually adding R squared to the Schreier transversal. And similarly, when we add S from RH, then we're adding RS to the Schreier transversal and RS inverse, and that gives us our spanning tree. But you can use any spanning tree. We could have used all but one of the blue edges, and then we would have the Schreier transversal of the powers of R. It doesn't really matter. The way that I've done it in the pictures is how it works in the program that I wrote. But yeah, any Schreier transversal is fine, any spanning tree is fine. And the transversal elements correspond to the edges on the shortest path from H. The Reidemeister-Schreier rewriting process is a procedure for finding a presentation for a subgroup H of finite index in G, and it's based on the following theorem, which is this long one here. So basically we've got U is our Schreier transversal. We've got this generating set B, which has all these things in it, and then our relations, we've got one for each relation for each element in the Schreier transversal. But we can do this whole thing on the Coset graph, and it's just far more intuitive, because I feel like this theorem is just kind of like confusing about why that would work. Whereas when you do it on the Coset graph, it kind of makes sense. To me anyway, hopefully to you as well. All right. So how does it correspond? The Schreier transversal is the Coset is the spanning tree, as we saw, and there's 9 edges which are not in the spanning tree. They correspond to the elements of B, the generators, and the set S is found by applying each relator of G to each vertex of the graph. So the edges of the spanning tree are labeled 1H, but I'm not going to write that because it makes it too confusing. But if we think about the path defined by the relator RS squared from the vertex H, we go from H to RH, and this edge is in the spanning tree, so it has the label 1H of identity. Then up to R4H, again, the identity, we have an unlabeled edge to R5, and the last S takes us back to H. So the relators always give us cycles, which if you think about how you make a coset table, that makes sense. And this here is a relator of H, which means that that unlabeled edge is an element of B that's going to be equal to the identity. So instead of using the label B, we can just make that edge the identity. Now, instead of oh, sorry, that's the next bit. We've got to talk about Seitz transformation. So basically what we've just done is a Seitz transformation. They're a family of procedures that involve adding or removing generators and relators from a finite presentation without changing the group described. So in the Reidemeister-Schreier rewriting process, we would get a really ugly presentation that we would then have to simplify with Seitz transformations. And in this procedure, we're sort of doing that as we go to try and get a presentation with the generators that we want. So we're using just one of the Seitz transformations. This Y inverse W is a relator and Y is not W, then we can remove the generator Y, which is what we did on the Coset graph. The idea of the relators being applied to each coset actually gets simplified because they're cycles. So for example, R8, it doesn't matter which vertex you apply it from, you're going to get the same edges. But as you can see, there's more than one unlabeled edge, so we can't do the same trick with this cycle. And at the moment, there's no more labels that can be found that way. So we're going to look at the cycles from each of the generators of H. Those are only necessarily cycles from the coset H or the vertex H. In this case, there are cycles from all of them because the subgroup's normal, but that's not necessarily the case. So our first generator of H is called W, and that's R to the 3 S inverse. So we look at the labels along the edges. The first one is labeled with the identity. The second one is labeled with the identity. Then we've got an unlabeled edge. And then our last step, we're going backwards along this pink edge. And that takes us back to H. So we've got 3 identity edges and 1 unlabeled edge. And we want the cycle to reduce to W. So all we have to do is label this edge W. And now the cycle reduces to W. This is like the easiest sort of case, but there are some more complicated cases. So if we look at X is R squared S inverse R from the coset H, we've got the identity takes us to RH. We have another identity edge to R squared H. Then we're going backwards along the pink edge and back down to H. So these three edges are all the identity, and our pink unlabeled edge is the one we're going to label. But because we went backwards along that edge, to get the cycle to reduce to X, we need to label that edge X inverse. And then we get the labels, the identity, X inverse, inverse, and then the identity, which is just X. When we label Y is S inverse R squared, that one's another easy one. We just have the one unlabeled edge, so we label that Y. And our kind of third type of labeling procedure we use for Z. So that's S inverse R3. The cycle looks like this. And in this case, we've got two identity edges, an unlabeled edge, and then the last edge is labeled Y. So to get the cycle to reduce to Z, we label that edge ZY inverse. Obviously, it doesn't matter what you label those edges, you're still going to get a presentation, but labeling them specifically like this gives us the presentation in the generators that we want, which means that we can use the Coset graph to get words in those generators specifically. Okay, so now we've labeled all the generators and we use the relations to label the rest of the edges. So if we look at R squared from RH, then that's this cycle here. We've got one unlabeled edge, and as this is a relator of H, these edges are going to be equal to the identity. So we can label that edge YZ inverse, and then the cycle just reduces to the identity. Next, we can look at R8 from R4H, where you can look at it from anywhere, but I've just chosen that vertex. So if we follow this path along, we've got the identity, then ZY inverse, and then Y. So now we're back down to Z as the label along this path. Another identity edge, another identity edge, the identity, and then W. So we've got ZW so far, and then our unlabeled edge. So we label this last edge with W inverse, Z inverse. And this is using those seats transformations to get the other labels. Okay, so then we've got, how am I going for time? Not good. All right, so we use the other relators to get the rest of the labels for our Coset graph. And there it is. So that's our labeled Coset graph. And then this is what we can use to get a presentation and also to find elements of the subgroup in terms of the generators that we've chosen. So to get, oh, yeah, I just wanted to say that, like, so the way that I've done it there is pretty simple, but in most cases, it's not actually that simple, and we have to experiment with temporary generators. Our procedure most of the time gets labeled Coset graph, but it can't be guaranteed. I think that it would be equivalent to solving the word problem if I managed to guarantee it. So I haven't even tried. To get a presentation from the labeled Coset graph, we know what our generators are. We already chose those. So then we apply the relators to each vertex, but we've already used most of them. So most of them are just going to reduce to the identity. In fact, in this instance, the only one we haven't used is the pink cycle, the S to the 8. So we just take all the labels along that cycle, and that's our one relator for H. I did this much faster when I was just talking to myself before. Okay, so that's our presentation for H. Then we can get words for elements of H in those generators just by following the path and taking the labels along the path. So if we do R inverse, Z to the inverse R4, then we go backwards along the blue, backwards along the pink, and then forwards along there, and that's our cycle. So when we multiply those all together, we get W inverse. Anyway, so we did that for all the conjugates, and that shows that the group is normal. And it looks like a lot of slides, but it's just because we're only doing one thing at a time. So the rest of the results for maps of genus 2 to 12 can be found on my GitHub. You can also find the code for the program there. And that's it. Thank you.
Thank you. Does anyone have any questions?
Just at the beginning with the definition of orientable and regular maps, what were the flags? Just can you say a little bit about how they're defined?
So the flags are the triangles in the bariatric subdivision. It's sort of like the arcs, but it's a little bit more complicated.
So it's like a surface that's cut up by the label that you've the graph that you embedded in the surface or something.
Sorry, what was that?
So the map is sending a graph into a surface.
Yeah. And then we've cut up the face of the map.
Yeah.
You take the bariatric subdivision of that, and it gives you right angle triangles, and it's transitive on those, just slightly different to being transitive on the arcs.
Okay. I probably need to
Yeah, it's better to look at a picture. I think there's a pretty good picture just on Wikipedia, so
okay.
Sorry.
No worries.
I don't have a picture ready. Any more questions?
I guess my question is just how quick is your program at like computing these labeled Coset graphs?
It really,
I guess it depends on the groups that you get.
yeah.
But yeah.
It not only depends on the groups, but it also depends on the generating set that you choose. But the thing is, if it's taking a long time, then the labels that you get are going to be long and awful. So what I did, if it starts taking like 5 minutes or so, then I just pick a different generating set.
Okay. Yeah.
And then that'll give me, it'll finish quicker and I'll get nicer labels.
Cool.
But yeah, so I mean, yeah, it really depends, but a lot of the time it'll be almost instant.
Nice. So if nobody else has any questions, let's thank Georgina again.